Welcome to Ask and Learn.
One-half mole of an ideal gas is taken from state A to C as shown in figure P19.34. A, calculate the final temperature of the gas. B, calculate the work done on or by the gas as it moves from A to C. And C, does the heat leave the system or enter the system during this process? How much heat, and explain. Okay, so let's take some notes. I'm going to copy down the diagram, and I'm going to first write down 2 that N is 0.5 moles. And then here's our diagram. Kind of goes like this and this. And that's 0.003, 0.004, and then that's 0.002. And this is 4 times 10 to the 5 pascals. So, here's P and V. And then here's pascals. And then this is in units of meter cubed, both SI, so that's great. We don't have to do any additional unit conversions. Great. And then there's 2 and 4 times 10 to the 5. Okay, so the first question asks to compute the final temperature. So the great thing about a PV diagram is we have P and V, and we have the number of moles, so we can straightforwardly get the final temperature using the ideal gas law. So if you rearrange the ideal gas law, you get T in general is equal to PV over N R. And then I'll put a subscript for C because this is all at C, and N and R stay the same. So I will not put subscripts on that. Great. And P at C is 2 times 10 to the 5 pascals. V at C is 0.00, not 000, just 004 meters cubed. And you want to divide this whole thing by 0.5 mole and multiply by 8.31 joules per mole Kelvin. And what we get is, if you plug that all into a calculator, you get 192.5 Kelvin, or at least that's what I got. Great. And for part B, it asks for the work done on or by the gas as it moves from state A to C. So to find the work, you always find the area under the curve of the PV diagram. So I'm going to highlight that area, and you can do that sort of by breaking it into like a triangle whose length is 0.001 and whose height is 2 times 10 to the 5, and then take the area of that, and so it's just half times those 2 quantities that I just mentioned, and then the area of a rectangle is just length times width. And so so the work is just going to be equal to the area of the triangle, and so that's 100 joules, and then the area of the rectangle, and that's 400 joules. And I can also write out how I got those numbers. So the 100 joules came from 1/2 times 200, not 200, 2 times 10 to the 5 pascals, and then the width is 0.001, and then the rectangle is 2 meter cubed, and then that's 2 times 10 to the 5th pascals times 0.002 meter cubed. And then if you stick that in a calculator, I think you'll get for this quantity, which is 500 joules. And I'm going to box that answer, and while I'm thinking about it, I'll go box the answer from part A. And so let me reread C. Does heat leave or enter the system during this process? How much heat? Explain. Oh, I also realized I wrote B twice. I'm gonna erase that. Okay, back to finding heat. So for C, you want to find the heat. As always, we use our sort of energy conservation formula, which is delta U. The change in internal energy is Q minus the work done by the gas. And we can, delta U is going to be 3/2 NR delta T. But if we look at how we calculated the temperature, we did this PV over NR, and then the numerator had 2 times 10 to the 5 times 0.04 times 10 to the 5. Now, if we calculate the initial temperature in the same way, the numerator, instead of 2 to 10 to the 5 and 0.004, it'll have 4 times 10 to the 5 and 0.002. And the product of those are actually the same, which indicates that, which if you calculate it, you'll get the same initial temperature as the final. So even though it changed temperature during the process, it actually ended at the same temperature. Okay, so then we know that this is equal to 0. And so now we know that Q is equal to the work done by the gas. And so let's think about the signs here. I talked about, in B, I talked about finding the work by finding the area under that curve, but I didn't say anything about the signs. If the volume overall increases, then the sign is positive. And if the volume decreases, then the sign is negative. So our volume increased, so our work is positive, and therefore our Q is positive. And so heat had to flow into the system. And precisely 500 joules had to flow into the system. So I'll just write it explicitly, and then I'll write like into the system. All right, there we go.